It will be in newtons per meter squared. So remember, you do the same calculation. You don't have to do this 144 thing because it's already given in pascals, consistent units. But the gamma of water is 9806. Remember the 9806 we saw in the previous example? That's what you use right here. That's a specific weight of water. Anyway, in the case of US units, the answer comes out in feet. So this pressure of 60 psi represents 138 feet of water column, of a water column. Okay, that's the head. So if you were to take a 138 foot of water column, measure the weight of that column at the bottom of that column, you'll end up with a pressure basically in pounds per square feet or pounds per square inch, 60 psi. That's what that pressure represents. Essentially, it's the weight of the water. Then Z, of course, you don't have to convert. That's already in feet. It's in elevation. The velocity is the other one. In order to convert that, we do V squared over 2G. That's the kinetic energy head. Notice what happens in this. First of all, use consistent units, please. That's very, very important. In this case, velocity must be in feet per second. And V squared over 2G is shown right here. It's 6.4 squared divided by 2 times 32.2, which is 2 times G, gives you 0.64. Now, if you look at these numbers, remember the Bernoulli equation, I mentioned three terms. P over gamma plus Z plus V squared over 2G. These three terms together represent the total energy of that fluid at this particular cross-section. If you look at these three terms, the most dominant one, of course, is elevation. Of course, that's related to a datum. But if you look at these two terms, P over gamma and Z, they definitely are a lot larger in magnitude than the velocity head. So in many, many pipe problems, we tend to, if we neglect this velocity head, you'll be fine. So keep that in mind because in some situations, some problems, the velocity may not be given, but you have to pretty much assume that the velocity head is going to be small or negligible. So you can go ahead and apply the Bernoulli equation. In pipe problems or water supply systems, this is very, very true. Most water supply engineers will track the changes in P or gamma plus Z combined. That's called by the way, that's called the hydraulic head or the piezometric head. Okay, so keep that in mind. They track that because the velocity head to them is fairly small, the changes in that. So in this case, the total head, if you add all three, is 639.14 feet. And then I took the liberty of converting that to energy or power. In this case, gamma QH. In order to calculate power, you have to be given the Q, the flow rate. It is a function of that. The more the flow rate, the more the power. So the same amount of head, as in this example, if the flow rate was doubled, then the power will also be doubled. That should tell you something because in turbines and when you run turbines where you generate power, it's a function of both the amount of head that's available to you as well as the flow rate that is going through the system. Gamma, of course, you can't do much with that other than change the fluid. But right now with water, it's 62.4. So here's the calculation. Unit of this computation will come out in what? Pound foot per second. Okay. As I said, horsepower is a preferred unit. If we divide by 550, it scales to 450. Okay, so this example shows you all these various quantities. Also, I want to go with this because sometimes in some questions they ask you the definition of or the quantification of what we call the hydraulic gradient line or the EGL, energy gradient line. They call them AGL or EGL. All it is at any cross-section of the pipe, at any point in the system, they want you to plot the sum of these two terms. P or gamma plus Z term is called the hydraulic gradient line at that point, or AGL at that point. If you sum the kinetic energy also into it, then the sum of all three is called the energy grade line, or EGL. So all these lines represent is what the total energy is or what the total hydraulic grade is at a particular point in the fluid, okay? So keep that in mind. Of course, for an open channel system, you'll have to substitute P or gamma and substitute Y, the flow depth for that. So therefore, for an open channel system, the hydraulic gradient line is Y plus Z. Now, if you think about it, what is Y plus Z? It's basically the flow depth, vertical flow depth, plus the elevation of the channel bottom above a datum. So that's essentially what we call the stage or the water surface of the channel system. So it takes you to the water surface of the channel system. So therefore, the hydraulic gradient line in an open channel is the water surface. Okay, so if you take a boat and ride along a river system, you're riding along the AGL. You can't do that in a pipe system because the pipe system is under pressure. I've set up a small example to show you how Bernoulli equation is used. Let's go through this small example, and typical problems will be like this, where they'll ask you to analyze, determine some unknown quantity. Now remember, if you use the Bernoulli equation, you can only have one unknown, because since you have one equation. So in this case, a pump delivers an oil. Now keep in mind, it's an oil, it's not water. The Q is 5.62 CFS, specific gravity is 0.762. From a reservoir A to reservoir D, the loss of energy, in this case the head loss, I'm going to give it to you. Next time I'll show you how to calculate them. And then from B to C is also given. So I'll kind of go through this a little bit fast because we've got to cover a lot of material here. So essentially what I'm going to do is, to apply the Bernoulli equation, I select 2 points. The most logical points to pick in this case would be point A and point D, because both at these 2 points, the water surface in the reservoir is what I call a free surface. The gauge pressure there is 0. And also the velocity head is negligible in reservoirs. So one could therefore write the Bernoulli equation between A and B and be able to solve for whatever unknown. In this case, what I would like to know is the head delivered by the pump to the water system and its horsepower. So a pump is delivering water from A to B, A to D, and we're trying to find out what that head delivered by the pump is. So what we do is we simply write the Bernoulli equation between point A and point D here. And here it is. PA over gamma plus VA squared over 2G plus ZA represents the total energy at point A. Plus any head delivered to the system. Doesn't matter where the pump is. This simply is an energy budget equation. So plus head delivered by the pump minus any head loss. Now remember, you're going from point A to point D. And therefore on the right hand side must be the total energy at D. PD over gamma plus VD squared over 2G plus ZD. I suggest you write the whole equation, and then you can always neglect or equate to 0 whatever quantities that need to be. For example, PA over gamma is 0 because it's a free surface at point A. The velocity head in a reservoir typically is negligible. It's very small. ZA is 50 in this case. The datum, height above the datum is given. Remember, point A is at the water surface, right? You're shown by the triangle there. The head delivered by the pump is unknown, so I'm going to call it H pump. Of course, the two losses between section A and section D is 8.25 plus, this is given the head loss, 21.75. So add them together, and that's due to friction, minor loss of whatever you may have. And on the right-hand side, PD over gamma is again 0, velocity is negligible, and the height of point D is 200 feet above the datum. So if you put it all together, the head delivered by the pump is equal to 180 feet. Why is it 180? Well, it's equal to essentially the elevation difference between A and D, which is 200 minus 50, which is 150, plus any head loss that it has to overcome. In this case, that head loss is 30 feet. So 150 plus 30 is 180. So it makes sense that the pump has to deliver 150 feet of head in order to take the oil or take this fluid water from one end to the other. In order to convert that to horsepower, by the way, this is an oil. Here's the computation. Gamma of oil is specific gravity times 62.4 times Q times H. There's your power that is needed in order to make this fluid delivered from A to B. In terms of horsepower, it's 87.46. Now, they'll always throw in an efficiency term sometimes. They'll say the pump is 80% efficient. What should be the horsepower of the pump? Well, the way I look at efficiency is, if you keep in mind that this is the amount of energy that's delivered to the fluid, if the pump is only 80% efficient, it has to have 20% more horsepower in order to deliver, correct, to overcome the losses within the pump. So you divide by 0.8 to get the true horsepower of the pump in this problem. Okay. So efficiency, I don't want to give you a formula. It's best to handle it logically by remembering what each of these terms represents. Okay, moving on. And here I've taken the liberty to plot the EGL and HGL we just discussed for the same system. Please review this on your own time. And I've set up a nice problem for you to apply. I strongly recommend you work through this problem because I've had previous participants run into some problems. I'll be happy to answer any questions. You can email me, particularly this number 3, because this asks for basically the pressure intake at point B. So that kind of forces you to write the Bernoulli equation between A and B. Remember, I was trying to avoid that because the pressure at B, it's an internal point, and there is pressure there, PB or gamma, and that's an unknown. So you'll have to use the Bernoulli equation between A and B. Of course, the head loss is given, remember. I already gave you from A to B is 8.25 feet. So given that, go ahead and write the Bernoulli equation and solve for the pressure at point B. By the way, there's a concept of, in pumps, when it comes to pumps, there's a process called cavitation of pumps. That will not happen in this system because the gauge pressure will be positive here. Usually that's an issue or concern if that pressure there drops below the vapor pressure of water. I won't get into that. That's maybe an advanced topic for the morning session. But if you want to know about it, you can always read a little bit on pumps or pump hydraulics. I've also set up another example for application of the Bernoulli equation open channel systems. Let's, for example, the total energy, let's do this one. Here, its velocity is given at that section V1. The depth is Y1. By the way, this is a rectangular channel, it's 8 meters wide, and the elevation head is Z1 is 100. So can you go ahead and tell me what the total energy H1 is at section 1? Now remember, in the Bernoulli equation we have 3 terms. Instead of P over gamma, you'll be substituting Y, the flow depth. Somebody asked me, do you have solutions? Well, I will give you on a case-by-case basis. I don't have the solutions. I do have the answers, though, posted at the back of my presentation. I'll show you when we get there, the last slide. So I do have the answers for these problems, okay? I would like you to attempt them, and then if you run into a problem, I'll be happy to give you the solution. So it's always good to try them out first. Okay, the answer to this, somebody's already coming along with this. I don't see 100.81 on my answers here, one of my options. I don't know how this gentleman got 100.81. The ones are A, B, and C here, and D. Anybody come out with that answer? Remember, Z1 is 100. By definition is Y1 plus what? Z1. That's already 104. So you cannot have 100. And plus V squared over 2G, okay? So please, whoever that gentleman is, might want to work it again. The total energy for this particular cross section. The answer will be, give you a few minutes. Alpha is 1, by the way, so you don't have to worry about that. For those who forgot the equation, I'll go back one slide, maybe a couple of slides. This is the equation right here. The total energy in an open channel system. Okay, remember Y, the flow depth Z, and V squared over 2G. Alpha is 1 here. Okay, in any case, I cannot wait too long, so we'll proceed. I'm sure you can work this out at your leisurely. The answer, by the way, in this particular case will come out to be C. Okay. Let's move on to some pipe hydraulics now. We want to, one of the things they'll probably ask you in many problems is to compute 2 types of losses in pipes. One is called the friction loss, the other is minor loss. This sets the stage for analyzing pipe systems. Typically the total loss is the sum of the 2. Friction loss is basically occurs throughout the pipe. It's a function of basically the pipe itself and the fluid flow. Minor losses are usually due to fittings, such as